Hello everyone, to the fourth module of this course. Today we are going to talk about spontaneous parametric down conversion, which is one method to create non-classical quantum states of light. In the first modules we discussed basically what are individual photons, we discussed how they interfere, and we also discussed the property of entanglement. And now we are going to discuss one method that can be used to create these entangled states, which is called spontaneous parametric down conversion. What this is all about? The central element here is a nonlinear optical medium, typically some crystal, which has to have a second order nonlinearity here denoted by the chi2. And what we do for the spontaneous parametric down conversion, we will send photons into these nonlinear crystals, and we will call these photons now pump photons. And then due to the nonlinearity, these photons can decay into pairs of photons, just as in this little animation. In the nonlinear crystal, a pair of photons is generated from the original photon, where the resulting photon pair consists from a signal photon, the red one, and an idler photon, the blue one. The names of these, they come from the history of nonlinear optics, but we adopt these throughout this presentation. That's a process that classically is not supposed to happen, because all the pump photons essentially are in eigenstates, plane waves for instance, of a certain frequency and polarization, and they are not supposed to change their eigenstate on their own. However, the nonlinearity in this nonlinear medium, that creates a perturbation of the system, and due to this perturbation, different eigenstates of light can be coupled, and the pump photon can couple to the modes of the signal and idler photons, which happen to have different frequencies. And now the question is, first of all, what are the properties of the resulting photons or photon pairs, and how we can control them? And the answer is very much in this particular type of interaction. We can control a lot of the properties by controlling, in the end, the properties of this nonlinear medium and controlling the properties of this interaction. Before we do this, let's look at what actually determines now these properties of the photon pairs in spontaneous parametric down conversion. They are basically, so first of all, they are characterized by two parameters. One is the frequency that I already mentioned. So we have these pump photons here, which have a frequency omega p, the signal photons omega s, and the idler photons have a frequency of omega I. And we know that these frequencies essentially are connected to the energy. The energy of a photon is h bar times its frequency. And since energy conservation has to hold universally, that puts a condition on the frequencies of these three photons, namely that the frequency of the pump photon has to be equal to the sum of the frequencies of the signal and idler photons, or the energy of the pump photon has to be equal to the sum of the energy of the signal and idler photons. And this basically is one condition that has to be fulfilled, a condition on the sum of the frequencies of the two photons. Importantly, this is not a condition really on the individual frequencies. As long as the sum condition is fulfilled, the frequencies of the signal and idler photons, they are free. And additionally to this energy conservation is a second condition, which is now a condition not for the frequencies, but for the propagation constants of these modes and of these photons. So we know that each of the modes, assuming that it's a plane wave, for instance, that each of the modes here is characterized by a wave vector. And turns out that there is a similar conservation relation as for the energy, also for these wave vectors, in the sense that the wave vector of the pump has to be equal to the wave vector of the signal and the idler photons, as sketched here in this diagram. They can be now in all directions, and that's why also the signal and idler photons can propagate in different directions as the pump to fulfill this condition. So, and since this wave vectors depend on the frequencies through the dispersion relation of the medium, this phase matching condition in turn also controls the frequencies at which we can efficiently generate photon pairs. It's not as strict as a condition as the energy conservation. I mean, energy conservation always has to be fulfilled strictly, at least in all realistic systems that we look at, whereas the phase matching condition has to be fulfilled to reach maximum efficiency. If we have a phase mismatch, so the sum of the signal and idler wave vectors is not exactly the wave vector of the pump, we can still generate photon pairs, but with a smaller efficiency. What does this mean in practice? Well, here is an example for a particular crystal. On the left side, there's basically a calculation of the emission probability amplitude. Now that's a somewhat complex plot, that's why let's explain it. So on the bottom, we have here the wavelengths of the photons that can be emitted. And here we have the angle under which they can be emitted. And we fixed here the pump wavelengths to something in the order of 400 nanometers. And then what we can see under an angle of 0 degree, well, we have here a maximum at 570 nanometer corresponding to the signal wavelengths and a corresponding maximum at 1570 nanometer corresponding to the idler wavelengths. So in forward direction, an angle of 0 degree, we have emission of a photon pair which consists of two photons, one at 570 and one at 1.5 micrometer wavelengths. And then at other angles, we can have also emission of photon pairs. However, they will be emitted at different wavelengths because there the phase matching relation are fulfilled for slightly different wavelengths. And that in an experiment would lead to images like this. So that's now from an experiment in exactly this type of crystal, beta barium borate, BBO, where people use the camera to image the visible part of the emitted photons. And here you see that, well, under different angles, there are different colors, different frequencies emitted, with the higher frequencies emitted at larger angles, just as shown here, that the shorter wavelengths come out at larger angles and the longer wavelengths on that part of the spectrum, they come out in the center, like here. So that's now the simplest case, that we have like one dominant emission direction, and then we have cones of different frequencies around this emission direction. Now, if we want to have entanglement, then we always need, let's say, two possibilities for our two photon state to emerge, and that can be achieved in a similar way also in a BBO crystal. So here's now a sketch on the left side of a slightly different situation where basically the crystal orientation was changed, which changes the phase matching condition. And what is happening in this situation is the following, that we have, this crystal here is in the center of these cones. We pump it from the backside, so the pump is in the middle of all these things. And then instead of one cone of phase matching, we always get now two cones, where always the signal photons and the idler photons are emitted in these two neighboring cones. And well, if we now again do such a camera image now with three different filters to see basically the rings that are resulting from these cones on the camera, what we will see is here now three different, let's say, photon pair possibilities. One is this inner ring where, let's say, one of the photons is red and the other one is blue. So it has two different frequencies. Then a case where both of them have the same frequency or wavelengths, so both of them are green circles. And then a case where now the frequencies are changed, so we have a blue circle here at a different angle and a red circle here. Yeah? So, and all this is symmetric around this point here in the center, the optical axis, where the pump light is basically sent through the crystal and through this complete optical system. Yeah? And if we now focus our attention just on the two green circles, this is now sketched in this slide, then we can find a case where we can actually generate an entangled state. For this, we have to know one other important property, which we did not discuss. Yeah? And this is now the polarization of these photons that are emitted. And it happens that in this particular phase matching configuration in this BBO crystal, yeah, we have basically always one polarization in one of the circles. So here, vertical polarization, and the other polarization on the other circle. So horizontal polarization. And that means now that the photon pairs that we emit, yeah, where always one of the photons is on one of the circles and the other photon is on the other circle, that these photon pairs always consist of one photon being of vertical frequency polarization and the other being of horizontal polarization. Yeah, and here with these dark dots and dashed lines, I mark two possibilities. Yeah, so photon pair vertical horizontal or vertical horizontal. Yeah, so and now we focus again just on these two spatial points where these two curves overlap. Yeah, and in this point we have the situation that if we put filters there and just look at the photons that are passing through the filters at this point, yeah, let's say tiny pinholes, then we see that there can be basically two possibilities of photon pairs that can be detected. And one is that we basically have a vertical photon up here in this point number 2, yeah, on the solid circle, and the corresponding horizontal photon on the dashed circle down here in mode 1. Yeah? Or we can have the opposite case, that here we have the horizontal photon on the dashed circle, or here we have the vertical polarized photon on the solid circle. Yeah? And if we now write this in the language of our quantum states that we discussed in the earlier modules, then we find exactly the state that we have down here, yeah, that we can have either one photon vertically polarized in mode 1, yeah, through this pinhole number 1, and the corresponding one photon horizontally polarized in the position 2, or the other way around. Yeah? And if we do this with exactly equal probabilities or probability amplitudes of 1 over square root of 2, then we create a state which is maximally entangled, yeah? Which basically in this lazy physicist form can be written as exactly this VH plus HV, yeah, which is one of the maximally entangled so-called Bell states. Yeah? And with this, well, I would end this module today, where we try to introduce spontaneous parametric down conversion and try to discuss how to generate entangled states with it.